Hello, hello. So today we're going to talk about why stoichiometry works. I think this is a basic principle that we deal with, and I think it might be better if we clarify why we do the certain operations we do, why we do the certain conversions, and why we have the certain parentheses that we have. So before we even get started, I want to take a look at our mole island diagram. That's something that you may have seen before. And you'll notice that we have a couple things like grams of a substance, moles of a substance, particles of a substance. You also have grams of a different substance, moles of a different substance, and particles of a different substance. So this diagram allows us to go from one substance to another. But one of the key aspects about it is these little parentheses here, and I'm actually going to add a couple just right here and here. So the key aspect are these parentheses. They tell us the operations that we are doing to whatever our starting value is as we move through and get our other values. But one of the questions I get is, why are these parentheses these parentheses? Why is it the atomic mass over the mole, and specifically 1 mole? And why in other equations we don't even have a number of moles listed? We have to use the coefficient from a balanced equation. So we're going to go over why it works. And the first thing I want to talk about is stoichiometry really, more than anything, is just dimensional analysis. That's basically the process where we convert one thing into another. I'm going to move this whole thing down. So it's basically dimensional analysis. It's how we convert one thing to another. And if I gave us the problem where I have, let's do it like this, where I have days, and I want to convert 4 days to seconds. So if I want to convert 4 days to seconds, well, what I can do is I can convert days to hours. I can convert hours to minutes, and I can convert minutes to seconds. And these are each individual conversions that I can generally do pretty well. We know that for days, we can take our unit. 1 day is equal to 24 hours. We know that 60 minutes is equal to 1 hour. And we know that 60 seconds is equal to 1 minute. And doing these conversions, we see that we can multiply our 4 days by 24. So we'll multiply 4 by 24 by 60 by 60, and we'll get some amount of seconds. And when we do these conversions, it's pretty easy to see why. We're just taking these conversion factors, being 1 day equals 24 hours. We're taking 1 hour equals 60 minutes, and 1 minute equals 60 seconds. We're taking these conversion factors and putting them into this conversion. And the beauty of that is we're not actually changing anything except for the units. We are converting days to seconds. And they're still equal to the same amount. 4 days is still equal to whatever this is in seconds. Stoichiometry is literally the exact same thing. So when we talk about stoichiometry, we still need our units that we're converting to. We still need our, for example, days, hours, minutes, seconds, but instead we're actually going to be dealing with, just going to get rid of all this stuff. Instead of days, hours, minutes, seconds, we might be instead dealing with grams of A, moles, moles of B, grams of B. And we're doing the exact same conversion. So I'm going to go ahead and take my mole island. I'm going to move it out of the way. And if we want to, for example, convert grams A to grams B, we're going to do dimensional analysis just like we did with days to hours. So we start with grams A. I'm not gonna make these neat circles. And for grams A, we're gonna then go to moles. And we can see that because of our nice mole island. We gotta go grams A to moles A, moles A to moles B to grams B. And you might ask yourself, well, what are the conversions? Well, we'll talk about that in just a minute. So for grams A to moles of A, what we have to use here is we actually have a conversion factor. Just like before we had 1 day is 24 hours, here we have what's known as the molar mass. And the molar mass basically tells us that 1 mole of any substance is equal to the atomic mass in grams of that same substance. And so if we're converting grams to moles, we need to make sure that the conversion factor has both grams and moles, and this one does. Just like we had day, and hour, we have now, sorry, I'm going to keep the colors consistent. We have now atomic mass grams of A and 1 mole of A. So our conversion factor has a mole, and it also has a gram and a gram. Whatever unit we start with comes down to the bottom, and that actually continues throughout the whole thing. Just a quick heads up. If we're starting with days, then we have day on the bottom. I'm going to switch to a brighter color. We're starting with, oh, too bright. If we're starting with days, then we have day on the bottom. Then we have hours, then we have hours on the bottom. Then we have minutes, then we have minutes on the bottom, and we end with seconds, which is the unit we want. So here we have grams on top, grams on the bottom. So if we have mole on top, our next conversion must have mole, specifically of A, on the bottom. And we can see that we have moles of B over moles of A. So we're going to be going to mole B. So moles of B over moles of A. And we'll fill in those numbers in just a moment. The last thing is mole B to gram B. For mole B to gram B, this one's a little bit the same as what we've done before, but a little bit different. So once again, we have our conversion. So we have the same thing. 1 mole is the atomic mass, except now, before we had started with grams and we were starting with grams and going to moles. So grams was on the top, grams is on the bottom. Now we have moles, we're going to grams, so mole has to be on the bottom. So 1 mole of B is equal to the atomic mass grams of B. And that's how we do any stoichiometry, and it's going to work exactly the same. The last thing that you may have to ask is, well, you never told us how many moles of A and how many moles of B, because you might have noticed I said 1 mole here and 1 mole here. I always tell you the moles, and this chart even always tells you the moles. It's always 1 mole, or on the bottom we have 1 mole, 1 mole, 1 mole, and 1 mole. But in this middle section, I don't tell you the moles. Well, here's the secret. The moles here, these are the coefficients from a balanced chemical equation. So just for a quick example, if our chemical equation is 2A plus 3B reacts to form 4C, or you know what, let's make it more realistic, 4AB, so a combination of the two. You know what, this isn't even balanced. Sorry, now I'm getting pretty upset with how I made a completely unbalanced equation. This would be A2B3. So the coefficient of A is 2. So we would actually have 2 moles of A. And the coefficient of B is 3. So we would have 3 moles of B. And that's how we fill in those. So you definitely need a balanced chemical equation. If we end up looking at everything, these steps for stoichiometry are the exact same steps for general dimensional analysis. The only difference is now we're using chemicals and our conversion factors are molar mass, and specifically this here, right, this in the middle is called the mole ratio. That's what this is. So our conversion factors are now molar mass and mole ratio instead of conversion factors you use every day, like seconds to minutes, minutes to hours, hours and days. But overall, it's still the same thing. It's all dimensional analysis. Hopefully this gave you a little bit of insight on stoichiometry and how it works. I'll be doing some practice problems in my next video with some real numbers. Thank you.